Welcome to Daily Papers, the podcast where we break down the latest research into bite-sized conversations.
Today, we're looking at a paper that asks a really simple but profound question about artificial intelligence. We all want our AI assistants to be smarter, faster, and cheaper. But what if the way we're trying to make them smarter is actually making them slower and more expensive?
It's a bit of a paradox, and it's at the heart of this paper from researchers at the University of Central Florida and Microsoft Research, titled, "Are We Scaling the Right Thing? A System Perspective on Test Time Scaling."
Okay, there are a few big words in that title, so let's unpack it. For years, the main rule for making AI better has been something called scaling laws. The idea was simple. Bigger is better.
Right. If you wanted a smarter large language model, or LLM, you just had to scale everything up. Use a bigger model, feed it more data from the internet, and train it using more powerful computers. It's like building a skyscraper. The taller you build it, the better the view.
And this worked. It gave us the incredibly powerful models we have today. But the paper points out that our relationship with AI is changing. We finished building these giant skyscrapers, and now we're all living and working inside them every day. And we're starting to realize that running the electricity and the elevators in a mega skyscraper is incredibly expensive and sometimes a little slow.
This is where test time scaling, or TTS, comes in. It's a newer, cleverer idea. Instead of just building a bigger model from the start, TTS is about making the model you already have think a little harder when you ask it a question at test time.
I like to think of it like this. The old scaling law was about building a more and more powerful calculator. Test time scaling is like giving your current calculator a piece of scratch paper and a bit more time to work through a really complex math problem. It uses its existing resources more effectively to get a better answer.
It's a great idea, but this paper argues that researchers have been measuring the success of TTS in the wrong way. They've been obsessed with something called the compute optimal Pareto frontier.
That sounds incredibly technical.
It does, but the concept is pretty straightforward. Imagine a graph where the bottom axis is compute power used and the side axis is how good is the answer. The compute optimal line is that perfect, beautiful curve on the graph that represents the absolute best possible answer you can get for any given amount of computer power. It's the theoretical limit of perfection.
So researchers have been trying to get their models to operate along this perfect curve. But the paper's killer insight is that compute optimal is not the same thing as system optimal.
Exactly. What's optimal in a lab on a graph isn't what's optimal for you, the person waiting for an answer. As a user, you don't care about a theoretical curve. You care about two real-world things. First, how long do I have to wait? That's a metric called latency.
And second, how much did it cost to generate this answer? Because someone, somewhere, is paying for the electricity. That's cost per token, or the price for every word the AI produces. The paper argues we should be focused on making those two things better.
So to prove their point, the researchers ran an experiment. They took some AI models, gave them a bunch of tricky math problems, and tried out two popular speed-up techniques to see what would happen to the real-world latency and cost.
The first technique is called speculative decoding. This one is really cool. It's like having a hyperactive junior assistant and a wise, experienced boss. The junior assistant, a smaller, faster AI model, quickly scribbles down a draft answer. Then the big smart AI boss just glances over it, makes a few corrections, and sends it off. It's much faster than the boss writing the whole thing from scratch.
And did it work?
It did, but only up to a point. It gave a nice boost, making the model faster and more accurate initially, but eventually the benefit flattened out. You get diminishing returns. There's a limit to how much you can improve just by drafting quickly.
Okay, so what was the second technique they tested?
This one is called tensor parallelism. That's just a fancy term for a simple idea. Throw more computers at the problem. If one computer chip or GPU is too slow to run the giant AI brain, just split the brain across 2 or 4 or even 8 GPUs and have them work together.
That seems obvious. More hands make light work. It should be faster and better, right?
That's what everyone thought, but the results were genuinely surprising. For these complex reasoning tasks, adding more GPUs often made the system less efficient. The cost per token went up, and the latency didn't improve as much as you'd expect. In some cases, it was even worse.
How is that possible? How can more computers make something slower?
The paper suggests it's because of communication overhead. Think of it like a group project. With 2 people, you can work pretty efficiently, but if you have a team of 8 people working on one document, they end up spending half their time in meetings and sending emails just to coordinate who is doing what.
Ah, so the different GPUs were spending so much time talking to each other to stay in sync that it actually slowed down the real work of solving the math problem.
Precisely. The coordination cost became a bottleneck. So what looked like a great idea on a theoretical compute optimal graph, just add more compute power, was actually a bad idea from a system optimal perspective. It was more expensive and not much faster for the user.
So the big conclusion here is that the way we measure better AI might be flawed. We need what the authors call a paradigm shift.
Right. They're urging the entire field to move beyond just chasing theoretical perfection and start measuring what actually matters to people. Forget the abstract graphs for a moment and focus on the 2 simple questions. How fast can I get my answer? And how much does it cost? Because someone, somewhere, is paying for the electricity.
It's a call to build AI that is not just powerful in theory, but is also practical, efficient, and useful in the real world. It's about optimizing the entire system from the moment you hit enter to the moment you get a response.
It's a great reminder that sometimes the most powerful idea isn't the one with the most complex equation, but the one that asks the most simple, common sense question.
That's all the time we have for this edition of Daily Papers. Thanks for tuning in.